Dear students, today we will discuss the next chapter of distributed database systems, that is database integration. So we have just finished database design and now we're starting database integration. So it is important to know the problem definition. And if you go towards the problem definition, it says that given the existing databases with their local conceptual schemas, how to integrate the local conceptual schemas into a global conceptual schema. And the global conceptual schema is also called the mediated schema. If you just recall your previous knowledge and or if you go through with the previous lectures, which have already been uploaded, according to them, that whenever we talk about a distributed mechanism, so we always go with the local conceptual schemas, which are basically based on all those fragments which you have identified by a design strategy. Now, whatever the design strategy is, either you go for the horizontal partitioning or you go for vertical partitioning, either you go from for applying, either you go for the primary horizontal fragmentation or you go for the derived horizontal one, or even you go for the vertical fragmentation by applying, let's suppose, the bound energy algorithm. In any case, you turned up with the proper fragments, and obviously for all those fragments you have to design the local conceptual schema. And when I say local conceptual schema, that always resides at a particular site. So how to integrate the LCS? So let's suppose in this situation what the problem is. Let's assume that we have decided that we have three local conceptual schemas for our given problem. So the question is that all these local conceptual schema obviously resides on the sites which you have identified, but how they will be integrated? Because at the end of the day, you're talking about an integrated system. And in that integrated system, we have already discussed that there is a transparency because all those users who are making queries to the system or those systems who are running various applications on this model, they perceive that database or your system as a single system, and obviously those integration is very important, and whenever we perform that integration, actually it becomes the definition of the global conceptual schema. So global conceptual schema is not, you can say itself is sort of a schema which is residing somewhere, but actually it comes up with your integration strategy. So once you define those rules, once you define that integration mechanism, that global conceptual schema comes into existence, and that makes sure that there is no violation of integrity rules or other rules while you are executing queries. So that is why that global conceptual schema can also be defined as a mediated schema, because by using that global conceptual schema, you mediate. Let's suppose a query is being generated by any user sitting at any site. So that global, actually it is being evaluated or semantically evaluated, first of all, with the definition of the global conceptual schema. And later on, it can be divided into subqueries that can be routed towards the sites where your LCS is. Because whenever we have an LCS definition, we always have the local internal schema. So it means that data is actually residing at that particular site rather than at one site. So for that purpose, normally the bottom-up design process is used. Why? Because here we are talking about the LCS, and by combining those LCS together, we can formulate the definition of GCS. So it is that is why that is called a bottom-up design process. So there are two alternatives we have. One is through physical integration, and the second one is through the logical integration. So both these strategies practically are there and are and normally used in various systems. So once you when you say the physical integration, it means the source database integrated and the integrated database is materialized. So it means that the source database itself is defined and the integrated database has to be materialized as well. It means that you can run various applications on it, or the data is actually saved in the system. So all updates are to be performed within that system. So it means that we have that physical link which is there among those databases, whether we are talking about the source one and the integrated one. So let's suppose we have a big source and we have other databases which are, let's suppose, which are required for that particular source, and all those databases are then physically linked with the source databases, and then the source database can use those databases as well for running various applications or for running queries or online queries. And that strategy is normally used in data warehouses concept. So if you have an idea of data warehouses, that works in that manner, because there we have the data which is defined in terms of various, let's suppose we have the main source and then we have the data marts, and and then we go for OLAP or online analytical processing applications, or and then we can integrate all these various databases to the source databases. So that is basically the concept of data warehouse right now. The other option we have is called the logical integration. So actually, when we talk about the global conceptual schema implementation, so global conceptual schema itself is not physical. That is why I told you earlier that we never said that GCS is residing on one computer. No, GCS is not a physical entity actually, and it is not residing somewhere, because if GCS itself is physical, then it means we are not talking about a distributed mechanism. It means then again it will become the centralized mechanism. So here it is distributed mechanism. So GCS itself is there, but it is virtual in nature. It is not physical. How it emerged? It emerged with the help of the integration strategy we have. So if we have that integration strategy, let's assume that one database is running at the finance side regarding the student, or one database is running at the semester cell for your data, and one is there in the enrollment section, all these section involving the student data. And now so that they are working separately, but let's assume that we have a task that we have to integrate these three files together, or three databases together. So now what we do is, if we go for the logical integration, then we will try to develop the integration rules, procedures, and then we'll try to define those rules in such a manner that the definition of the GCS emerged. Since there is no need to make a physical arrangement or physical integration in that case, because if you do so, then you will not going for the distributive mechanism. You're not talking about the same schema which we have discussed in the previous chapter. There we have the GCS definition and LCS definition, and then we have seen there various architectures for their representation as well. And that is also called EII, that is called Enterprise Information Integration. So whenever we are working in any enterprise, we might have various databases running at various ends. So there is need to integrate them rather than to centralize, to come out with a centralized idea, or come out with the with the approach where you make the homogeneous, make all these databases homogeneous, and then you develop the the main schema, and then you divide the main schema. Then you will not go with this process. Actually, you go for the integration process. So data warehouse approach, as you can see that we have the ETL tools which are there to access that data, and we have the materialized global databases. There we normally call it the materialized global database, where we have all those updates which are there. So here we are not talking about only views. Here we are not talking about only the virtual definitions. Here we are talking about the materialized. It means actually all those updates are to be performed. Actually, it is there. Record all of these are actually recorded on the physical drive at that particular site. So if we have the materialized global database, then we have certain tools. What these tools will do? These tools will integrate all various databases which are being used for that data warehouse approach. Because when we talk about data warehouse, we are talking about various data resources which are there, and we try to link all those resources with the materialized global database, so that various online processing tools can be applied to access that data, or to process that data, or to filter that data. But that basically is the data warehousing approach. So when you talk about the bottom up design, where you call the GCS as your mediated schema, is defined first. So what we do is define first, map the LCS to this schema. So what we have to do? So once we want, if we want GCS to be our mediated schema, that is our task. So what we have to do? We have the LCS definitions with ourselves. Maybe you have three LCS, maybe you have four LCS, maybe you have five LCS in your problem, whatever the problem is. But to the task is to map the this schema LCS to this schema. So let's suppose if we have three LCS, we have to perform the mapping, as in the data warehouses. So GCS is defined as an integration of parts of LCS. So generate GCS and map LCS to this GCS. So the other way is to make a generalized definition and then do the mapping. Or the first thing is map those LCS into schema. That is two ways by which you can do it. Let's suppose you have the generalized definition, and then you confirm that all those LCS maps to it. So generate GCS, a global conceptual schema, and map LCS to this GCS, or direct map LCS to this schema. So both strategies are there in terms of bottom up design approach. And that represents or give you two types of relationship between GCS and LCS. So what are these two types of relationships? Please give a time to understand this concept. So we have two types of relationships. One is called local as view, and the other one is called the global as view. And you can see the diagrams as well on the screen. The figure A represents the global as view, and the figure B represents the local as view. The GCS definition is assumed to exist. It means that if you talk about a local as view, you believe that initial definition of GCS is there, and each LCS is treated as a view definition over it, and all those LCS you will take in that particular problem is treated as a view definition. Is basically representing a view, is representing a subset of the representation of the GCS, in other words. Or you can say it gives you the partial data which is there, which is the representation in LCS in the form of the view. So in local as view, the GCS definition is assumed to exist. That is important. So we believe first that the GCS definition is there. The objects expressible as queries over the GCS. So the all the objects are being defined, are expressible. So whatever the objects which are defined in the given database are expressible. It means you can access it, you can run such an application which can use this. Uh, Global as view represents, as you can see, is defined in global as view. The GCS is defined as a set of views over the LCS. Now, here the difference is that here first we have the LCS definitions, and then GCS is defined on those views which are being represented by LCS. So only the matter of perception. So both look as view and global as view basically works on the GCS and LCS, but how the model is developed, or you can say how the representation is done, or how that integration is managed. Actually, that is the difference between the two. In the local as view, the GCS definition is pre-assumed, and then you will treat LCS as a view definition over it. But comparatively, in the global as view, the the GCS definition is based on the given LCS. So once you have those LCS, only then on the basis of this you can drive the definition of GCS, because it is actually a virtual definition. It is not the physical definition. So that integration process itself is represented in this model, and how this model works, you can see yourself that it's a bottom-up process or bottom-up integration, and therefore you can see that you start from there on the bottom, and let's assume that you have various database resources, and those various database resources are represented in terms of various schemas, as the database one is schema, two schema, dot dot dot, and schema. Depending on the problem you have, you might have two schemas, you might have more than two schemas. It is up to the problem. So, and because what is the actual task you have? The actual task is to integrate it, to come out with the GCS definition. So let's suppose if I am running three various databases, like I have given you one example, that in the university, one data regarding the student is managed in the semester cell, one is in the enrollment, and let's suppose one in the fee section. And all these three are different databases running in the same organization. And let's suppose if we want to integrate them, so there are three various databases running and we want to integrate them. So number one, so first thing what we have to do is that we have to convert them, we have to translate them. So whatever the database is, you need a translation. How that database will be represented, because every database has, has its own definition. Every database has its own tables. Every database has its own description of attributes, so on and so forth. So we need a translation for every database. So we have to be translated. That has to be translated, and then actually, after that translations, it moved towards the schema generator part, which is very important. And here you have three steps. One is called the matching, the second is called the integration, and third is called the mapping. This we will discuss in detail in the coming slides. But if you try to understand the concept, that is very simple concept. Uh, Whenever you want to integrate these three databases together, so might the data is represented in the semester cell is let's suppose in a different format, let's suppose having other attributes which are not represented somewhere else. But let's suppose if I want to match the same entity, a same student having a seat number B15001, B15001, so that B15001 has to be mapped, has to be matched in all these three databases, because that has to be there, because that entity is there in the university. So if that entity is there in the university, doesn't matter whether it is being managed in the semester cell or in the enrollment section or in the fee section. So that is to be matched. So actually that matching is done with respect to all those entity information which are being which are being represented in various databases, maybe the personal information, maybe the contact information, maybe the program information, because if your data is there in the semester cell, so it is relevant with a specific program, and obviously you have the enrollment of that specific program, so enrollment must know what programs you are in right now. And similarly, the fee section exactly know that which program you are studying, because the fees are based on the various programs the university offers, either in the morning or in the evening, or it's a diploma program or a BS program or an honors program or a master program or a postgraduate program or a PhD program. So that data has to be matched. Obviously, when we go for the matching, we come out with problems, we come out with issues. Why? Because the representation might be different, because all these databases were originally running, differently, and obviously the design is different. So obvious, it is quite obvious that the representation is different. So sometimes when we go for the matching, we have issues. How we can we make sure that the same representation is there, and and the same representation is there in the enrollment, because of certain attributes. Sometimes for example, for sometime the father name is or the name of the student is completely represented, like Muhammad Ali bin Salim, but maybe the data which is there in the fee section, there it is only mentioned Muhammad Salim. So it means we have, when we match this, we have to see that whether we are matching the same entity or not. It is very important. So whatever the data you have, let's suppose here I've given you the example of student files. Let's forget about the student. Let's suppose if you have three various stores running in various cities of Pakistan, and you have three inventory stores, and let's assume that these inventory stores were previously managed independently, and now you want to integrate them. So here you have to make sure how the item representation is there. So item is being represented in obviously there are certain specifications, there are certain parameters or characteristics in which these representations are there. So when you match them, you have to make sure whether they are matched or not, whether they are same or not, because basically you want to develop the GCS definition. So first step is matching. Now, for matching, we have various strategies which we will discuss later on. One, two, three. There are various ways by which we can match. For example, you can match by using simple natural, for example, using NLP process or NLP algorithms. You can see the various statistics, and then by applying NLP approach, and you can give a statement whether they are the same or not. The second step here after the matching is the integration. So then you develop a rule, or you format a rule once it is matched, that let's suppose they are the same. So if they are the same, then they are representing as the same entity. So if they are representing the same, then they will be integrated, and obviously once it is integrated, then it is mapped. And once the mapping is done, mapping means that you exactly know, okay, this entity reflects this table reflects this entity, this relationship reflects this constraint, so on and so forth. So if you have all those relationships developed, all those for example, the correspondence between various entities is completed, then it means that your mapping is done. And once your mapping is done, that schema will the global conceptual schema may be generated. So then we might have the global definition of the student, then we might have the global definition of the results, then we might have the global definition of the fee information, then we might have the global information of the enrollment data, and then these three databases, if they are integrated, now they can work in the same manner. Otherwise, if they are running separately and you will not apply any matching mechanism or integration mechanism, then actually you cannot come out with the definition of GCS, and then actually you cannot use these you cannot make a distributed application. So if when we talk about a distributed system, it means a proper distributed system. We talk about a proper distributed database management system. We are not talking about the remote handling of files. The one solution might be that all these data are there in the respective section, and I'll apply the remote processing, and then I can even match the data and I can check the data. But I'm not talking about that. I'm talking about a pure database application. So by doing these three steps, we can formulate the definition of global conceptual schema. And just to recall your architecture section, which we have discussed earlier on, the talked about various kinds of distributed architectures. So one architecture which we have discussed earlier on is called multi distributed database architecture or multi-database architecture. Here you can see that you have a GCS definition, and on the bottom you can see you have the LCS. You might have LCS 1, 2 till you have LCSN, depending on your own problem, in which obviously which you want to integrate. And for every LCS you can see at the bottom that you have the local internal schema. Why there's a local internal schema? The reason is that all those database handling is then done at the localized site. So that data has to be saved at that particular site. So the physical schema must be there. The physical schema must be defined at that particular site. Okay, so we have LIS, then we have the LCS, and then you can see, because we're talking about a multi-distributed database architecture, so here you can see that every LCS might have their own external schema as well. What does it mean? It reflects that there might be some data which is there at that particular localized site, which is only used, which is only accessed by the users which are there at that particular site. So you may define a localized external schema as well. So that localized external schema may be developed for that particular databases. So it is not necessary that all the time that all the data which is there is must have a same external schema. So you might have various external schema definition based on the given local conceptual schemas, and that actually happens in a real life situation. So then all these LCS will come up to formulate the definition of GCS, which is not a physical entity. Rather it's a virtual entity, and which is developed by the definition of the LCS. And every GCS has its own generalized external schema as well. So you might have a generalized definition of the external schema, or global schema. Normally you call it global external schema. So you might have the definition of the global external schema, which is based on the GCS. And in this is the just the recall of the access architecture. So in the database integration issues, the first thing is the schema translation. We just talked about in the diagram. So schema translation refers to what? Is a component database schema translated to common intermediate canonical representation. So whenever we talk about translation, it means that whatever the database which you want to translate has to be translated into a common intermediate canonical representation. You might come out with some representation which is common to all those databases. For example, let's suppose you picked up the data model of the semester cell, and then you picked up the data model of the enrollment section, and then you try to come out with an intermediate model where all these representation can be defined. Okay, schema generation. Intermediate schemas are used to create a global conceptual. So once you have that intermediate schema which is matched and translated, then it can be used to develop the global conceptual schema. And there are various ways by which we can translate the given model. For example, let's suppose if the databases are developed by using the RDBMS approach, so you can use the relational model as well. And in the relational model, you can use the relation schemas. Let's suppose if you have a relation structure, then you have the tables and you might have the constraints. So try to develop the intermediate schema which represents all the tables, all the relations which are there. The other way by which you can do it, it is entity relationship model or ERD model. So ERD model also help you to translate the given database, and that is also a canonical representation. So might have that ERD representation where it shows that where the database is translated, so that we can have a similar representation. So if we don't have the similar representation, then obviously translation is difficult, because if we have three various definitions of an object, then how we can translate it? Then the translation will be difficult. So obviously for that purpose, we need to have any canonical model which we want to use. All of these are termed as the canonical models. And let's suppose if you're talking about object oriented environment, then you have to have the class model, or ARTIMS tool can be used. If you are graph oriented, let's suppose you are not talking about a proper relational model or ERD model, you might represent this in a graph, and you can see that whether the translation is same or not. And obviously if you translate all these three into a graph form, then you can easily match them. So where various approaches are there, even a few people might generate XML schema, and then they can see by converting the given database into an XML schema, and then they can also translate it. Mapping algorithms. So we go for the schema generation. So for schema generation, we have three steps, as you have seen in the model. One is called the schema matching. The second one is called the schema integration. And third one is called the schema mapping. I just recall the model. You can see here schema matching, schema integration, and then the schema mapping. Okay. So here the same thing. The schema generation, we have the schema matching, means finding the correspondences between multiple schemas. So when we match, what we do? We find the correspondence. Let's suppose student number EP15001, whether it is there in the enrollment, whether it is there in the fee information. So that is the correspondence. Let's suppose that EP15001 is in BS Computer Science. So if it is BS Computer Science, that the same correspondence, whether it is the same correspondence is there in the enrollment, or the same correspondence is there in the fee section. So when I talk about correspondences, it means that we are talking about certain entity, and maybe the information pertaining to particular entity. So existence, actually it looks for the existence, that if that data is existing in a particular section or at one site, that whether it is available on the other site or not. So finding the correspondence between multiple schema, because if there is no correspondence between the schema, we cannot match it, because it means that they are different. So if they are not matching, they are different. So the second is creation schema integration. So creation of GCS or mediated schema using the correspondences. Let's suppose I have checked the student information, and in all these three sections, we have that information available in terms of their seat number, their name, and their father name. So I will come up with the GCS definition based on these correspondences. So I define that, okay, the seat number is defined in that manner, that which already matched. The father name and name is matched. So it means you can identify the entity on the basis of the seat number, as well as the father and name, and the name and the father name, and might be the contact. So, or might be the NIC information. So that will help me to create the GCS definition. Schema mapping, how to map data from local databases to GCS. Sometime in the GCS, is defined first, and schema matching and schema mapping is done against target GCS. You have many ways to solve your problem. Some In some cases, we have a good idea about the overall system, so we might generate the GCS. For example, the same problem which I just mentioned you about the university, so we have a clear idea that what will come in the GCS. So in this problem, I might have my mind clear, and I have the GCS definition with myself. So no problem. You can have your GCS definition and then you can match and map it. No problem. Or the other way around. So that is up to you. So the running example which we will use for this integration um, chapter is regarding the employee project assignment and pay. And here you can see that let's suppose if I have such a database, it can be either represented in the form of relational, as you can see on the left hand side of the screen, where the employee is represented in terms of a table and tables, and on the right hand side the same model is represented in terms of model. So both are the canonical representations. It's up to you. Either you can use the graphical model, either you can use the algorithmic model, either you can use the XML model, either you whatever model, or if it is object oriented, you might go for the class diagram, maybe, where that is a good representation. So it all depends on the model you are using. For example, here we are, because we are talking about distributed databases, and we are mostly talking about the relational data model. So therefore, these two models are relevant to us. So when we go for schema matching, these problems might arise. Number one, that is called schema heterogeneity. And there are two types of heterogeneity. When I say heterogeneity, it means difference. Heterogeneous means that when you try to match two things, you will come out with, okay, there is these two files are not matching. Let's suppose I take a file from the semester cell, I take a file from the enrollment. And they might have different attributes. They might have the additional information. They might have less information. One section may have one attribute, the other section might not have that attribute. One section might have take a different key to form. They have a different key for their data file. The other section might have different keys, so on and so forth. So if there are, obviously there is an heterogeneity. So whenever there is an heterogeneity, so heterogeneity is of two types. One is called schema heterogeneity, based on the schema, which is structural heterogeneity, which can be handled easily comparatively. But when you have heterogeneity in terms of meaning, representation, semantics, then it is difficult to manage. But in both cases, we can manage it. So once what is the structural heterogeneity? It is basically based on the given structure. For example, in one table, the student is represented represented with various attributes, and you might have type conflicts. So in one thing is represented in the form of numbers, might be on the other side it is represented in the form of character or a string. One thing which is represented in terms of date, somewhere it is the same thing is represented in terms of string, somewhere it is represented the same thing is represented with currency, and on the other side it might be represented in the form of the number. So these are type conflicts. Then sometimes we have dependency conflicts as well. So the dependence on one attribute to the other is representing differently in one relation at one site, and when we match it with the other side, they have a different dependency relationship. You might have various keys. So maybe in the semester cell they use the seat number as a key, but in the enrollment section they might take the enrollment number as a key, or they use NIC as a key. For example, for the in the payments in the fee section they take the NIC as a key. So they might have various keys. So there might be a key conflict as well. And behavioral means representation of those things. So might be different representations by different name. The second thing is called semantic heterogeneity, which is difficult to understand because it is easy to understand the type conflict. That is not a big problem, big issue. You can easily find out. But semantic heterogeneity is different, more important and harder to deal with. So sometimes you use synonyms, sometimes you use homonyms, hypernyms. You might have various ontologies, different ontology. For example, Semester Cell has designed the databases using XML, and on the other hand, the data is represented in the form of relational database. On the third side, the data is represented using the object-oriented approach. So now there are various totally different models, totally different approaches. They might have totally different ontology, means representation. So in one section, you might have totally different ontology. The data is defined. When I say the ontology, it means the representation of various entities and their relationships. And sometimes we have imprecise wording, so not clear. So how it is, they are using the short forms, and from the data it is not clear what that form is representing. For example, a student, and then it is written P1. I don't know what P1 is, what P1 is representing. So sometimes we have imprecise information, incomplete information as well. So it is difficult for us to understand what it represents, and that is why it comes under semantics. So there we have to spend some time to know exactly that whether these are the same things or not. So one thing might be represented in a different way in one section and a different way in another section. So it's up to they might use the Boolean attribute to for a certain attribute, and on the other section they might have some values to represent that attribute. So that is something which is difficult to understand. That is why it comes under semantic heterogeneity. The other complications in schema matching includes the other insufficient schema and instance information. You don't have the complete information. You have the insufficient schema. So then there is a problem because you have to come up with a complete schema. Sometimes you don't have the details. You have the data running on the site, but you don't have the model. You don't have any document with yourself to explain that what how it is working, what is the actual model. And then the subjectivity of the matching. So you can match two things like ABC, match ABC, but the problem is the subjectivity, what ABC is representing over there and what ABC is representing over there. Sometimes it makes a difference. Issues that affect schema matching is number one, the schema versus instance matching. Rather, we direct match the schema, or we take any instance and we can match it. So taking an instance means that you can take a certain instance, for example, a particular student in a particular department in a particular program. So you just take that instance and then you try to match it with the enrollment, and you try to match it with the fee section. So that is instance matching. And otherwise, you take the complete schema and then you map it, whether that schema is there or not. Element versus structural level. Take a particular element or a value, or take the complete structure. So when I say the structure, it means the complete representation. For example, table can be the representation, and that is all the complete representation we have. And then the cardinality, matching cardinal, how many times that appears, how many times that entity is represented in the semester cell, and how many times it is represent when it is matched to the entity which is there in the enrollment, how many times the matching is done. So let's suppose in enrollment section that record is appearing 5 times, and here also the record is appearing many times. When I compare it, how many times it is matched, is there any mismatching, how much mismatching is there. So we count them in terms of cardinality. So because that makes sure that whether it is the same entity or not. So I will conclude my lecture over here, and we will resume the discussion in the next lecture. Thank you so much.